good afternoon, everyone. I'm Jennifer Harpster. I'm the Science Section Head for the Science, Technology, and Business Division here. I'd like to welcome you to today's program that will take us to Mars, where we will learn about the recent discovery of organic matter that was preserved in a 3 billion year old Martian mudstone. Exclamation mark. Let's see. So it's my pleasure to introduce today's speaker, Dr. Jennifer Eigenbrode. As a sample analysis at Mars collaborator and participating scientist for the Mars Science Laboratory mission, she has focused on the in situ detection and preservation of organic molecules in irradiated sediments at the Martian surface, enable the search for life beyond Earth. So please join me in welcoming Dr. Jennifer Eigenbrode to.
Thank you, Jennifer, for that opening statement. And thank you all for coming today. This is a great opportunity. I love being able to share the passion that I have for the stuff that I study. I really do have questions that I want to answer, or I want to see somebody answer them in my lifetime. And one of them is trying to understand if there is life beyond Earth. And I think that looking in our solar system is probably one of the easiest places for us to start. But let me get back to our topic here. We're talking about organic matter. Organic matter that was recently discovered on Mars. Now, the first thing you might ask, what really is organic matter? Because let's clear this up in the very beginning. Organic matter is carbon molecules that are bound together. They usually have hydrogen, sometimes oxygen, nitrogen, sulfur, phosphorus. Those things are all put together, and they make these big molecules. Now, organic matter is not just one molecule. It's a whole bunch of molecules all put together. So think about yourself. Biology is all organic material. We might have the plastics, the wood in the chairs, the hydrocarbons that we burn in our cars and for fuel. All of that, that's all organic material. That's all organic matter. This is the type of stuff that we would expect to be left behind in a rock if life had ever existed. But it's not the only way of getting organic matter. Okay, so with that in mind, we're searching for organic matter on Mars. That was one of the goals of the Mars Science Laboratory. And what I'm showing here is an image of the Curiosity rover at one of our key locations. Now, where is that? Curiosity is in this yellow location here on Mars. All of the white dots are pointing out other places where we've had other landings for our previous missions. But Curiosity is near the equator. And it's in a place we call Gale Crater. Now, this crater is about 96 meters wide. I'm sorry, not meters, 96 miles wide. And the peak in the middle of it, which was formed when an impactor hit the surface, is about 18,000 feet tall. All right, so it's taken us a long time to figure out exactly what the story of Gale Crater is. But when we first picked out this location, we had a hunch. It really wasn't too much more than a hunch because all we had were a few images. We had a hunch that there might be evidence of a former lake there. Well, that was indeed the case. And I'll tell you, when we first came across these, the outcrops that you see in these first two images, these things are called fluvial conglomerates. And there are basically lots of rounded pebbles packed together in a random assortment. And when you get that type of a feature, it means that you had chunks of rock and they were passed through a tumbling type action to make them round. And to take some kind of a medium to do that, it had to be water. And this was the first time we're like, oh my gosh, we had a river. We have evidence of a river. And this is one of the deposits from that. And as we kept trekking along on Mars, we ended up in a place called Yellowknife Bay. And that's what the mudstones on the right-hand picture is from. And you see there are fine layers. These are the sediments that end up going into the lake and they trickle down. It takes a while. And they make these fine layers at the bottom of the lake. And then when the lake disappears, that turns into a rock. That is what we found. So we had a river and we had lake. We were right. Our hunch took us in the right path. Okay, and these sediments are everywhere. This is a beautiful picture looking towards, the dune field on the side of the mound that's in the middle. And all of those layers are from a lake. There's not this, the lake that we had in Gale Crater wasn't just there and gone. It came and went. And it may have been pretty shallow at times, and it could have been meters deep at other times. But we think that it was pretty extensive because there's about 2,000 meters of material of this type of sediment. It takes a long time to get that. So the idea is the entire crater at one point filled with water, all but that middle peak in the middle, because that peak is actually taller than the surrounding area. So when we think about that time period, Mars was actually more wet. Not the red planet we think of today, but something where there might have been clouds, more moisture around. Exactly what that picture was like, we don't know. But at least in order to have water at the surface for such a small planet, it would take an atmosphere of some sort. It would take lots of moisture being pumped into it and to keep that water there. Now, the interesting thing about Mars is that it doesn't look like Earth. It doesn't have the biosphere. And every reason we could think of, it's very similar to Earth, but it took a different path. Well, what was that? Let's do a comparison to Earth, because this is probably the most fundamental thing that happened to Mars that took on a different path than what we have on Earth. Earth, shown here, has a magnetic field. Because we have a core of liquid fluids, liquid rock, and it's moving around, it creates what we call a dynamo. Now, you can't see the magnetic field, but what it does is it's actually an energy that kind of deflects the solar wind that's coming in. And you can see that as the little yellow lines there. The solar wind is coming in, and that solar wind is a whole bunch of ionized particles, ionizing energy, ionizing radiation. And the magnetic field literally deflects it. So we don't experience much of it. We get UVB, we get a little bit of UV, we get some visible light and all that kind of stuff. We get that through, but we don't get the ionizing radiation, the really intense stuff. All of that stays outside because of this magnetic field. Now, Mars had one like this too. And we know that because we see records of it in the rocks. But Mars lost its magnetic field because the inside of the planet actually got stiff. It stopped moving around. So here is a bow shock that's created by a magnetic field in yellow. And when that bow shock went away and the magnetic field went away, the solar wind blasted the atmosphere away. And that changed Mars forever. At this point, when this started happening, ionizing radiation started hitting the surface. Now, what does that mean? Ionizing radiation is damaging. We are familiar with it because we're always told it's bad for you, right? It does damage to our DNA. So when we have radiation come in and it hits things like a DNA, this is shown here as a helix, it actually can break bonds. So this radiation, whether it's electromagnetic or a particle like a proton, it comes in and it doesn't care what it hits. It's not choosing what it hits. Whatever is in its path, it hits. And it's going to deposit energy, which can break the bond. It can deposit its mass, which can change the atoms. It can do all sorts of things. That's if it's direct. The indirect is, what if it hits something like a water molecule in the atmosphere? It may turn into superoxide type molecules, free radicals. And those free radicals can do subsequent damage to organic molecules. So we think of this in our own lives in terms of what it means for us biologically and for our medical purposes. But when it comes to a planet, it means that this ionizing radiation is coming down to the surface, non-selectively changing it, destroying things, moving things around. And if your organic matter is sitting there in a rock near the surface and all this ionizing radiation is coming down, it can change it. It can destroy it. So honestly, when we first proposed this, or when this mission was first proposed, we knew we needed to look for organic matter, but we didn't know we were going to find it because of this. But we did it anyway. This is Sam. This is the sample analysis at Mars instrument suite. It's about the size of a large microwave oven. And it is an incredibly complex instrument. At the time, it was the most complex instrument ever sent to another planet. And here it is, all packaged up, being put into the belly of the rover that I showed you earlier. And you can see everyone's in clean room suits. We call those bunny suits. They're trying to keep the contamination down to a bare minimum to make sure we don't bring organic matter with us that we don't want with us when we get to Mars. Okay, so what happens in SAM is we heat a sample up that we've collected from the surface, and it turns into gases. Those gases then go into what we call a mass spectrometer, and they ionize. Now, this is deliberate ionization. We're trying to break the molecules up, but we do it in such a controlled manner that we can predict how molecules will break. And we use that information then to tell us what the molecule compositions are. So what we get is what we call a mass spectrum, shown here. So you can see at the very bottom, that's a mass to charge ratio. That's the unit our data comes in. And we get a signal for different types of masses. Those are for each fragment from molecules. We can take that information together, and knowing how the instrument works, we can piece together what the molecule was. So in this case, it's thiophene, which is carbon and sulfur and hydrogen put together. And you're going to see thiophene again shortly. Now, the first place we got to where we found some evidence of organic materials of some sort was at Yellowknife Bay. And there's a picture of where our scene was. You can see John Klein and Cumberland. Those are the names of targets that we drilled. And these are lake mudstones again. The unit is called the sheepbed mudstone. You see Gillespie Lake and Point Lake. Those are different types of rocks that are packaged together here. But when we got to the sheepbed mudstone, that's where we thought we had gotten to. These are the sediments from the base of this crater. This is as low as we're going to go. This is where we expect to find those lake sediments, and indeed that's what we found. In those rocks, we came across molecules that are chlorinated. Now, I didn't mention chlorine earlier. When I talked about organic matter, I didn't say chlorine. I said carbon, hydrogen, oxygen, sulfur, nitrogen, sometimes phosphorus. Chlorine's usually not in there. But here we have chlorine attached to organic molecules. And there was only about 5 of them, including this chlorobenzene that's shown here. This was a fabulous discovery. It's the first time we've actually discovered organic molecules at the surface, in situ, at the surface. But we didn't know what to do with this data. It was the last thing that we expected to find. What does this mean? How do we interpret this? What's the scientific implications of this? We weren't sure, because this is not what we expected. This is not organic matter as we expect to find it in a natural system. So we kept driving. So you see here Yellowknife Bay at the bottom, and this is an elevation map. So we drove up the hill into what we call the Murray Formation, and we came across this location called Pahrump Hills. And you can see at the top there, our rover is way up there by Vera Rubin Ridge. It's actually past it at this point. But we drove many miles to get to Pahrump Hills from Yellowknife Bay. And you can see in the map over there, as the crow flies, I think that's 4 or 5 miles. It took us a while to get there. But when we got to the base of Pahrump Hills, we got to the base of the Murray Formation. And this is what it looked like. And to a geologist, not the best outcrop, but hey, we'll take what we can get when we're on Mars. We studied these outcrops for quite a while. And we chose Confidence Hills, Mojave, Telegraph Peak, and this location called Buckskin, it's out of sight here, as 4 places where we wanted to drill and look at the materials that were in those rocks. And these are all lake mudstones in this location. And when we got to Confidence Hills in Mojave, we had drill hole that looks like the one that's shown here. And you know what's fabulous about this? Is the planet is red, and that is gray. Okay, so when it's red, it's rust. It's oxidized. Gray is not necessarily oxidized. Maybe all that radiation hasn't destroyed everything that we're after. That was the first thought. Okay, this is a good sign. We don't know where it's going to go. Well, we got data. And I'm going to give you sort of an overview of what this data is without getting into specifics. on the bottom axis is sample temperature. Remember how I told you we're heating the sample? And then on the y-axis, we have intensity of that signal. And you see a bunch of squiggles. Now they're separated, and they're separated by mass. And I put some colors in there and everything. So don't worry about that interpretation. The point is that when you get over 400 degrees, we started getting signals that we could not explain by any other means to say that it's coming from Mars. It's coming from the sample. Okay, so every signal that we have past 400, 500 degrees, that's Martian. We can't explain that with our instruments any other way. It's not something we brought with us. Now, if you go to the lower temperatures, there are some complications, and we know that we can contribute that just from our instrument. But over 500 degrees, no, all these gases that are coming off, this stuff is from our sample. And so you see that I have marked some of them with circles and squares and some upside down triangles there. Those are all noting temperatures where a whole bunch of stuff came out all at once. That is the type of signal that we get when you combust, or no, sorry, that's the type of signal you get when you break apart organic matter with heat. We see this all the time. We have 60, 70 years of data experience in doing this. We know how to do it. We know what it looks like. So what I'm showing here is a bunch of signals to tell us about different types of molecules. And these are all the molecules that we detected. This type of stuff. These are all little fragments of things. So what you see over here on the side of these lines, the end, every corner of a little figure here is a carbon atom. And the line represents the bond between them. And we just assume that there's hydrogen all over that unless we note it. So those blue lines, that's carbon-carbon. The carbon-nitrogen is in yellow. In the green underneath it, that's 3 carbons linked together. Underneath that, it's 4 carbons linked together. Underneath that, down in pink, you got 5 carbons linked together. In the middle, those are all rings of carbon. So 6 carbons linked together in a ring with different things coming off of it. Okay, and then over on the side, on the far side there, we've got molecules that have sulfur in them. This is exactly what we would expect of natural organic matter. Doesn't matter where you look for it. Meteorites, natural stuff you find in rocks here on Earth, coal, there's so many things. This is what you expect. This is what happens. This is what you get. Okay, we're feeling better about this. And even on top of that, there's another type of experiment that we do. It's called GCMS. It's gas chromatography mass spectrometry. And in that case, what we do is we actually take the gases that come off after heating it, and we put it into this column, and the column literally separates it. So as the molecules go through, some of them go through faster than others. One by one, they go out the other end and into the mass spectrometer. So we actually separate every single molecule, and we can look at them individually. And when we do that, we get really good data that can clarify what exactly that molecule is. And on the top, I'm showing in orange dotted, that's a blank. That's when we don't have any sample in the system. In blue, there's a Mojave sample. And you can see I've got 3 molecules marked there. They're the sulfur molecules. And in purple and flipped upside down, that's the same GCMS type system here on Earth in our lab, operating the exact same way as the one on Mars. And notice that the peaks line up to the ones on the bottom. The first 3 peaks line up to the ones on the top that have the molecules marked. That is perfect confirmation that we know what we're dealing with. And we have mass spectra that help tell us exactly what those are. So we have 2 types of analyses that show that these molecules are there. Now what's important is about the carbon-sulfur. Carbon-sulfur molecules are predominant on Earth in the rock record. And it's taken years of research for organic geochemists to figure out that sulfur is the mechanism by which a lot of organic matter that we use in petroleum, in coal, is preserved for millions to billions of years. Sulfur is key to all of that. It doesn't always stay in that organic matter on Earth, but it may be the first thing that happens that keeps it from being destroyed and getting into the rocks in the first place. So we have sulfur. That's a key thing that probably helped preserve this organic matter on Mars, just like it does on Earth. But the other thing that probably happened is that this organic matter, clearly it's refractory. It's hard to chemically break it up. Otherwise, radiation would have broken it up, or oxidants in the rocks would have broken up. Something would have happened. So how is it that it prevailed? Well, we see two molecules here. I've got benzene and propane shown, two separate molecules. These are the types of things we observed, but because of the temperature at which we observe them, they're telling us, the data is telling us that it's coming from something much larger. Giant molecules, macromolecules. We call these kerogen. Giant stuff. When I say we discovered organic matter on Mars, this is the type of stuff that we discovered. Not directly, but we use the best methods you can to determine it's there. So where did this organic matter come from? Was it Martian life? We really don't know. And to kind of, shed a little light on this, we took a Jurassic Paleosol. This is an ancient soil from 150 million years ago. You can see there's an image of what that would have looked like back then with the dinosaurs and the giant trees, the sequoias. And here is the rock in the middle, and there's this thing called the Great Dirt Bed. We looked at that. It's just, it's a good candidate. We looked at that. It's old. It has organic materials in it. It has coal in it. And would you believe that we saw the same type of signals? Okay, this is good. This is cool, right? Same type of signals. Nothing that is diagnostically different. But what else is there? We looked at meteorites. So here's an example of the Murchison carbonaceous chondrite. This is the stuff that's floating around our solar system from when it formed, and it's raining down on all the planets. And it has been raining down on all the planets since the planets formed in the first place. Okay, so this is solar system material. It's not related to life in any way in how it formed. And we analyzed that using the same type of methods like SAM. And we got the same type of results of what we saw on Mars. And then we got a Martian meteorite. And we put that into the SAM type of analysis. This one is from a geological source. So rock processes formed it. No life involved. Rock processes. People have synthesized this stuff in the lab. We know it's rock processes. And it created the same signal. Okay, so you see there's a pattern here. The data that we have is not diagnostic of the source. It just tells us that there's organic matter there. We do not have enough information. That's where we leaves us. So our conclusion is that organic matter has been preserved. This is fabulous. We've got it there. It's been there for 3.5 million years in lake sediments. And it was preserved probably through macromolecules, some sulfur, and the mudstones certainly help. But the source of it is unclear. But realize that Viking went looking for organic matter 42 years ago, and it didn't find any. Well, we finally found some. Why is this important? Well, if Gale Crater contained life 3.5 billion years ago, we don't know that it did. But if it did, then perhaps there's fossils of that life still around. Maybe it's preserved. Because the organic matter is preserved, the fossils of that life could be preserved in it. We just need to come up with the right tools, or I should say suite of tools, and uncover those fossils and observe them. We've taken the first step in the search for ancient life on Mars. The other thing is this lake was habitable. We know that from other geochemistry. But it not only supported autotrophic life. This is the type of life that uses CO2 as its carbon source, carbon dioxide. It also supported heterotrophic life, the organisms that eat other organic matter, like us. We eat organics. Okay, so all the types of metabolisms could have been supported in this lake. So it's been more than 40 years since we started the search for life and the search for organic matter on Mars. Now that we have evidence of the ancient organic matters that are preserved, we are one step closer to determining its source. So what happens next? Well, we've got two rovers that are they're going to be heading soon to Mars. One is the ESA's 2020 ExoMars rover. And the key thing about this one is it's going to drill deep. Now we talked about that radiation. That radiation really does a lot of damage at the very top surface. And the further down you get, the further away you get from that radiation. Mars is an ancient surface. We're talking millions of years old. Tens of millions, easy. 100 millions, possibly. So the surfaces you see, those pictures, Imagine that's been like that for millions and millions of years. It's a lot of radiation, a lot of time. Drilling deep gives us an opportunity to get away from all that. I can't wait. I honestly cannot wait. And we have another instrument on there that can provide not only the similar type of information that we got from Sam, but even more extensive information that could tell us if there are fossils there. The other one is the Mars 2020 rover that NASA is going to be sending, and it's a caching rover. It's going to go around and it's going to collect little samples and leave them on the ground, and later we can go back and pick those up and bring them home. Okay, that's the plan. It's going to take many years for that to happen. There could be other missions going to the surface, perhaps ones that target very specifically if there is life there in another way. So we talked about how modern day Mars here was more like this ancient Mars. That's of the rock record we looked at. But everything I just talked about was for the ancient stuff. Let's go back. Let's talk about modern Mars for a moment. Okay, we just found organic matter in an ancient record. There could have been life on Mars 3.5 billion years ago that produced it or was using that organic matter. We don't know that it was there, but it could have been the case. Back then, Mars was much more likely to have supported life. If that life ever existed, what happened to it? It probably went into the subsurface, where it took taking refuge away from all that ionizing radiation and all the oxidants on the surface. But here's the kicker. Here's what we know about life on Earth. It lives in all sorts of crazy extreme environments. Here's Dalal in Ethiopia. It has pH of less than 1. And look at all that green slime in there. Those are cyanobacteria living happily in this crazy pH environment. Okay? Survival for 500,000 years in permafrost. Organisms surviving that long in a super cold environment. Here's Blood Falls in Antarctica. It's draining an iron-rich lake that is below the glacier, away from sunlight. And that is loaded with organisms. And then there's even the Atacama Desert, probably one of the driest places we've extensively studied, and it has microbes that they're barely doing anything. They're around, and they hang out. And then when the conditions are right, we're doing something, let's reproduce, let's make more cells and everything. And then, things got dry again. Let's wait. And then they do something later. Okay, this is what extremophiles are like. We know this from examples on Earth. We have this rampant biosphere here. Mars certainly doesn't. But Mars could have an extremophilic biosphere. Here's another example. I love this one. Chernobyl. They found this fungi, Cryptococcus neoforans. It lives off of gamma radiation. You take the gamma radiation away and it stops doing stuff. It thrives on it. It needs it. This is an organism that adapts to the radiation. Hey, maybe organisms adapted to some level of radiation on Mars, something that we're not used to. There's microbes living on the outside of the International Space Station. Okay, so organisms adapt, especially if they have a lot of time. So Mars changed. It had a lake at one point. It probably had environments closer to what we're familiar with, but today it's different. So perhaps there's an extremophilic subsurface biosphere on Mars. It's not the same as what we have here, but it could still have a biosphere. And there are places that we might choose to go look for it. Some of the examples that people talk about are these reoccurring slope lineae. This is a slope here of a crater, and there are seeps of water coming out, groundwater seeping out. So subsurface materials are coming out to the surface, and then they're draining down, and they take repeated pictures, and they can see those wet spots changing by season. Or on the other side here, we've got the exposed ice in the northern plains. This was exposed by the Phoenix lander. Ice today could have been wet ground in the past. Because one of the crazy things about Mars is that unlike Earth, it has an orbital, a tilt to the planet that's pretty shallow. Mars tilts a lot. So you can imagine when that axis moves back and forth, the seasons change dramatically. That wet spot, or that icy spot there in the northern plains could have been a wet spot many millions of years ago, or even hundreds of thousands of years ago, which would have been nice for life, especially extremophilic life, if it can tolerate that. And then this is the big one. We don't know if there's a Mars ecology. We don't know if it's in the subsurface or not. In the past or even now, we don't have those answers. We do not know. But what happens in the future? It doesn't matter if it's past or now. It almost doesn't matter. What happens in the future? We're going to send humans. Humans have a biome around them. We're going to be sending that to Mars, and we will do our absolute best to contain it, but there will be inadvertent releases to the environment. Okay, so whether we intend it or not, there will be some sort of life on Mars. And maybe it's going to die out because it doesn't like the radiation. Maybe it's not going to survive. Or maybe it will find a way to adapt in its own niche. And it's hard to imagine what that would be, but it's possible. We want to study that. And if there is a Martian subsurface life, what happens when the two interact? Are we going to be able to observe that? Do we have a chance to study that if it happens? It would be a lot easier to study something like that if we first knew if Mars had life. So honestly, it would be wonderful to do a really good targeted study looking for life on Mars now, modern day life, in some place where we think it was most likely to be, if it's there at all, before we send a human. Whether or not that's in the cards is yet to be seen. So we'll see. And with that, I'm going to bring this to a close and answer any of your questions.
In the question and answer period, when someone answers a question, if you can repeat the question. Yeah. Okay, do we have questions? You're speechless? You're processing?
Ask anything, really. Yes.
Can you tell me the radiation level? I came in late, so I didn't. Maybe you mentioned that, but level of the radiation on the surface.
Levels of radiation on the surface. Yes, we do know what those are because on the Curiosity rover, there is an instrument called RAD, and it actually did these measurements. And there's different ways of reporting that value, but if you take all of the types of radiations it measured, it was 76 millirads per day. Oh, geez, I might be getting my units mixed up. It was a number that we were not too surprised by. It's not very high. No. That's right. Yeah, it's not very high. But in this case, when you talk about exposure to that over geological timescales, it makes a big difference. Yeah. Uh-huh.
The atmosphere, then, do we know what it maybe was way back when, the things you're saying could have been, versus what it is today? What does it have now versus what was it?
That's heavily debated on what that was. First off, you had to have a warmer planet in order to have all the liquid water around. And in order to have a sustained body of water, you have to have a certain amount of atmosphere. And in order to sustain an atmosphere, particularly when the magnetic field is already gone, it means that you have to be pumping more stuff into the atmosphere than is being stripped away by the solar wind. So those types of details are starting to be modeled, but we just don't have enough information on it yet. I think that the MAVEN mission, which studied the upper atmosphere, really gave us a lot of insights into the possibilities of what happened as far as the loss of the atmosphere and how different ions actually interact with that atmosphere to make it go away. That's the type of stuff that makes the models possible. So now we're waiting for the models to give us a better idea of what it might have been like.
So do you think humans on the surface of Mars can do this search for life just as well or better than robots?
No. I think that they could do it in a combination with rovers, but not on their own. Because an astronaut, even in a suit that is super clean or as clean as I can get it, it's still going to have some inadvertent level of biology on it. So when you're talking about looking for extraterrestrial life, if you find something, you have to be able to demonstrate it's not from us. It's not, because otherwise we will always be skeptical of it. We'll always question it. So when we take an astronaut to do a study like this, the advantage is to have a rover go collect the samples and get them contained. The rover we can keep clean. Let the rover go out and get the samples. The rover collects them, brings them into a facility, a habitat of some sort that has a science facility, and then you engage the astronaut in the analysis of that sample to look for signs of life and understand it if it's there. And the advantage there is that you don't have to wait for an analysis to be completed and then send all the data back home, have humans look at it there, and then send commands back to respond to what the data was telling you. The astronaut right there on the spot sees it, responds, does next test, sees it, responds, does next test, sees it, responds, does next test. The amount of data and observations and the direction of all that is strategically such that it increases the science return by so many orders of magnitude. And that would be really, really critical for not just making us feel more confident about what it is that we're looking at, but if it does look like it might be life, learning something about it. It's really going to be a combination of the two. And honestly, in every single scenario I've ever heard people talk about, that's really what's involved. It's the two.
But the research can go on without humans for the time being.
Oh, yeah, absolutely. I am convinced that if you figure out what you want to study, what type of data you need, and the requirements for getting that engineers will eventually figure out how to make that possible with a lander or a rover, some kind of robotic system. So it's doable. We can do it. We absolutely can. And we're ready to. Missions are being proposed to do it. But there are huge advantages to involving astronauts at some point later in the whole strategic process. Did I answer your question?
And just to round that out, I mean, they wouldn't necessarily have to be at the surface. I mean, they could be orbiting Mars in a station rather than...
Oh, yeah. If you get the samples to them, sure. Or if they are able to engage on a very quick time with a rover at the surface because they're in orbit. Yeah. Yeah, we call that low latency science. It's it doesn't take much time. It's low latency between an observation versus a response from that observation and determining what to do next. Yeah. Right now, it's a long time. You got to send the data back to Earth. Have a team of scientists look at it. Takes a couple days. Then you respond. Yeah, it takes a while. There's a question in the back there. Yeah.
What's the current thinking about why Mars lost its magnetic core, etc.? Why did it lose it when Earth did not?
I've heard two cases, two scenarios, and I honestly do not know if they've been updated. The first one is that Mars is about a sixth the size of Earth. And part of the reason why Earth still has molten core, a liquid rock type interior, is because of all of the radiation, all of the natural radioactivity of the rocks produce heat, and that keeps it melted. Okay, so if it's 1/6 the size, it has that much less of the radioactivity happening and the heat that's generated from that. So it doesn't have a natural heat source of its own in the interior that's going to sustain it. The other thought is that perhaps the Helenius Basin, which is a gigantic crater in the southern hemisphere of Mars, it's huge. And it breaks up the magnetic field lines that we see in the rocks which tell us that there were these rocks that were deposited and made when there was a magnetic field, and then the impactor that came in and hit that area disrupted all of that and created this gigantic basin. Well, people have modeled what that impactor would be like, and it could have been big enough to disrupt the interior of the Martian core. perhaps that had something to do with it. Maybe it was a combination of the two. But honestly, that's about as far as that has gone in ideas. That's all we know.
But Earth has not experienced a similar impact.
No, the only similar impactor would have been maybe the generation of the moon. And at that time, that was so early in the formation of the Earth that it didn't have the same type of response. Yeah. So no, Earth has not gone through that.
You mentioned at the beginning that sort of was a hunch that that crater could have been the result of comet impact something. Is it possible that such a mass would have carried organic material with it, and that's what you're discovering as opposed to native Martian soil?
Yes and no. If a large impactor hit, having something that was loaded with organic material and having it that size of what was needed to excavate Gale Crater, that's something that we're not familiar with. It's not possible, but we're not familiar with it. A lot of times the type of impactors we get are other types of rocks that don't have a lot of organic material. But hey, right now everything's a possibility. And if that were to happen, that impactor would have broken up into little pieces, and it would have and it excavated the hole there too. So you have a mixture of whatever it excavated out of the hole and all of the impactor material. It all kind of blends together and gets scattered about. Then you have water coming in. Now, we do have evidence of some water flowing on the surface and coming into the crater, but we do think that most of that water actually came from below, because there's probably groundwater and ice down below when this happened. And when you had this impactor come in, it generated so much heat. We had hydrothermal activity. All that stuff melted, and all that water kind of seeped through the bottom and come up. So all of the stuff, all the rocks scattered about, including the impactor, could have washed in, blown in, and then been part of the lake sediments. That is possible. But we just don't know. I think that's where we're going with it. We just don't know. There are so many questions. People try and model this type of stuff, and having organic matter coming in from large impactors is not the predominant way of getting solar system related organic materials to the surface. What's more likely to have happened, if it wasn't organic matter initially from Mars, is that we have these things called micrometeorites. And it's like dust particles. They're super tiny. They're incredibly hard to collect and study. But anyway, these things are raining down, and they're so small that they survive getting through the atmosphere. These things have been raining down on all the planets since they formed. Well, those things have organic matter in them, actually quite a bit. And so while a few in a rock don't make much of a difference because it's just such a small amount of organic material, if you talk about having a lake and you're collecting stuff over many, many tens of hundreds of millions of years' time, it can accumulate. It adds up. And it's not just what falls in, it's what's blown in, or it's what's washed in. So it's possible that the organic material that we're looking at, that we found with Sam, is actually the stuff. I looked at the carbonaceous meteorite. It's the same type of stuff. It could be that. It could be this dust particles that came in from the solar system. Yeah. So, hey, but you know what? Whatever we think is happened will change in next 10 years as we learn more about Mars. It's part of the fun of this research field. Yes.
Are there any plans to drill elsewhere on Mars where it's not a crater, no impact?
Okay, so the question is, are there any other plans to drill elsewhere on Mars? And the two rovers that I mentioned at the end, both of them have drilling capabilities. And the Mars Curiosity rover that was the point of this study, it had a drill on it. Or I should say, it still does. But the difference is the Curiosity rover and the Mars 2020 rover only drill down 5 centimeters. It's a really shallow drill hole. But the ExoMars rover is supposed to go down 2 meters. I mean, that's huge. That's going to give us access to samples that as long as we get the samples out of the ground and analyzed, we are going to learn something important. We'll have to wait and see what that is. Now, there are other proposals out there to drill deeper into the ground in other locations. One is to drill into the northern plains. I know I showed you that picture of the ice. The Phoenix had it excavated with a little scooper, and it had shown there was ice not too far down. Well, there's a mission that's proposed to actually go and look at that ice by drilling deeper into it. So, and if that were the case, it would look for signs of life. It's designed to do that. But that is not funded yet, and it's still a TBD. We don't know what's going to happen, so we'll wait and see. There may be others. People are talking about drilling for multiple reasons, not just for science sake, but also for the sake of excavating water that could be used by our astronauts in the future. Yeah. Yes?
You said that there were some questions that you wanted to have answered. What are maybe a couple of them off the top? Would you like to
Yeah. I think some of the biggest questions for me are, does Mars host life now? It's such a critical turning point in our thought of that planet if we come anywhere close to answering it. If we go look in the places where we think it's most likely to be and we don't find it, maybe we look a second time. We don't find it. Wow. It's either something so drastically different than anything we expected and we looked in the wrong places, or it's just not there. And that gives us, it sort of takes off a question and allows us to move forward in new science directions. But until we get that answered, or at least make an attempt to answer it, it's like I have a hurdle in front of us. We have this block. If there is life there, the exploration of Mars will change forever. Completely different path. So to me, it almost doesn't matter which one it is. I just want to see it happen. I just want to be able to shed some light on that question. That's the big one. The second one would be, what happened to it? Why is it not a biosphere on Mars? And I've watched the discovery of extremophiles over the decades as a student and then a researcher. And the boundaries of life just keep going further and further away. And it's just astounding to think that organisms have found a way of adapting to so many different niches, so many crazy places that even physically we didn't think it was possible. But somehow they found a way of doing it. And they're there. Okay, great. So if Mars had a more rampant biosphere at some point because it had lakes, it was easier for life to survive if it was there, why did it not adapt to what's there now? Why did it not adapt to all that radiation? I would almost think that drill a little further down and you might see something like we do if we go to the Arctic. You crack open a rock and you look a few centimeters into the rock and you'll actually see layers of colored organisms in the rock. They figured out, get away from the worst stuff, but hey, this is a happy zone right in here. So, they managed to do something. I would think that Mars would have that. Those are the big ones. And then the other questions really are more about, well, where else in the solar system might they be? And we have these ocean worlds. And honestly, if we find evidence of life on an ocean world, it might be that it's a second genesis of life, completely independent of Earth's. And if we find that, or we find evidence of life on Mars, these are all ifs, then when we look out in the solar system, when we look out at the stars at night or through our telescopes like Hubble and our future one of James Webb, and we see all of these galaxies out there and we wonder about all those exoplanets, we think about there might be life out there, we'll actually have some footing, some basis to say, oh yeah, there could be life out there, or why would there be life out there if there's no life here elsewhere in our solar system? A likely place for it to be. It kind of stabilizes and it moves us a little bit further away from what we think, what we want to think, what we assume, to having some basis for understanding what's possible elsewhere in the galaxies, in the universe. I'm not going to see the answers to all this in my lifetime, but the next generations might.
The rover's looking for organic material, and if you're collecting samples and running through the mass spectrogram, is there anything about the inorganic materials that are there that can contribute to understanding why the organics are still there, or it's like, you're focused on a little part, but then
Yes.
there's a whole lot more.
So the question is, what's the role of the inorganic materials in the preservation of the organic materials? And that's a fabulous question. Earth is a system on its own. And every little package of Earth, whether it's a little rock or a leaf or ourselves, we are systems too. And all the stuff that in that system is related to each other in its composition and how it works. So if we think about that on Mars, Mars as a planet is a system. Every bit about it influences the other bits. And if we zoom in on a rock, or even the crater, like Gale crater, or the rocks that we were looking at, and that organic material, that organic material is part of a system. And it exists because of the rest of that system, the rest of the composition, which is the inorganic materials. They most certainly have a huge impact on the preservation. And in fact, one of the things that I think the Mars 2020 rover is going to tell us is more about what that is, because it has the right instruments to actually examine the interface between the inorganic and the organic. So the minerals, how the organic matter is packaged within them. Does it tell us something about how the organic matter formed, or how it got sandwiched between minerals and then preserved? All of that is something that we need to learn a little bit more about. And the Mars 2020 rover is probably our first next step in making progress in that direction. The other way that we can learn about it is through meteorites. Luckily, there have been Martian meteorites, so pieces of Mars have landed on Earth, and we've been studying them. They've been around for decades. People have actually been able to figure out that they're from Mars based on their isotopes. And we've learned a lot. And because our instrument techniques on Earth keep advancing, we go back to those over and over again, and we learn more and more about them. But most of those, if not all of them, are from deeper in the planet rather than rocks like Gale crater. So they're not telling us about lake sediments. They're telling us about volcanic rocks deeper down. And that's important, but it leaves a lot of pockets that yet to be filled in our knowledge.